Welcome to Pomodoro Joe for Tuesday, March 28th, 2023. Today we're doing LeetCode problem 983, minimum cost for tickets. This is a medium problem. You have planned some train traveling 1 year in advance. The days of the year in which you will travel are given as an integer array, days. Each day is an integer from 1 to 365. Train tickets are sold in 3 different ways. A 1-day pass is sold for costs index $0. A 7-day pass is sold for cost index 1, and a 30-day pass is sold for costs index 2. The passes allow that many days of consecutive travel. For example, if we get a 7-day pass on day 2, then we can travel for 7 days, 2, 3, 4, 5, 6, 7, and 8. Return the minimum number of dollars you need to travel every day in the given list of days. All right, so this is pretty complicated. Yeah, this is complex for a medium problem. Okay, so we have 365 days. Some of the days we're traveling, some of the days we're not. We have 3 different options for buying passes: a 1-day pass, a 7-day pass, and a 30-day pass. That's a lot of different pieces, a lot of things to keep in mind. I think it's easy to try to jump ahead and say, well, let's find all the days in 30-day groups that have a lot of days that are consecutive. And it's easy to jump too far ahead and try to do a lot all at once. When I run into a problem like this where it seems really complicated, too many moving pieces, I try to break it down into smaller and smaller problems. So what's the smallest problem I can think of for this day? Well, let's just say it's day 1. So we're on day 1. What do? Do we buy a 1-day pass, a 7-day pass, or a 30-day pass? Well, it kind of depends. Are we traveling? So if we're not traveling on day 1, we don't buy a pass. There's no point in buying a pass if we're not going to travel. Even if we're traveling the next day, why buy a 30-day pass a day before you need it? It'll just end a day sooner. So if we don't travel on day 1, we don't buy a pass. Okay, that's easy. What about if we are traveling on day 1? Well, we could buy a 1-day pass, but then we might have to buy another pass the next day. So you kind of want to know if we're going to be traveling for the next couple days, but that can be complicated to try to figure all that out. So you can buy a 7-day pass, but again, it only makes sense if we're going to be traveling again in the next 7 days, and if the number of days outweigh the cost of buying just 1-day passes. Too complicated. So let's just do all 3 options. So that's my plan. On day 1, we have 3 different things we can do. We can buy a 1-day pass, a 7-day pass, or a 30-day pass. So let's just buy all of them, sort of. We'll explore the options. So we'll try option 1, we'll buy a 1-day pass, and then we'll see how much it's going to cost us from day 2 to the end of our travels. We'll also buy a 7-day pass, and then we don't need to worry about travel for the next 7 days. We can jump ahead to day 8 and see how much it's going to cost us from day 8 to the end of our travels. Or we can buy a 30-day pass, jump ahead to day 31, and see how much it's going to cost for the rest of our travels. All right, so that's my plan. So with that, we'll put 25 minutes on the Pomodoro timer and get started. So this is a perfect example of a recursive problem. So we will write a recursive function. Unfortunately, the function they give us is probably not the right function for a recursive function. It just gives us the days and all the costs. That function sets us up for a recursive function internally here. So we'll have our own internal function called min_cost_tickets recurse. So what do we pass in? We'll just pass in our start day. What day are we on? So now what's the first thing you do when you're writing your recursive function? You write your base case. So what is the base case? It's the case that we have where we're done with our work and we can just return. So how do we know we're done? Well, if our start date is outside of our travel days, we're done. So if our start is greater than 365, we are done. And we'll return 0. We're not going to spend any money to travel on this day. What else do we need here? Well, let's see. I guess we can say, are we traveling on the start day? I guess we could do something like this. If start is in days, then we know we are traveling. Or we can say if start not in days, Let's just do that. Okay, if our start day is not in our days, then we'll return our min cost tickets recurse for start +1. So we might not be traveling today, but we could be traveling tomorrow. All right, and now it's time for the fun stuff. At this point, we have three options. We have a day, we're traveling, what do we want to do? Well, let's try all three options. So option A. Option A, we're going to buy a one-day pass. So that's going to be our costs at index 0. And then we're going to find out how much it's going to cost for the rest of our travels. So that's the min cost. So that's the min cost tickets recurse for our start +1. So that's the next day. Option B. We're going to buy the 7-day pass. So that's cost at index 1 plus the min cost. Start +7. So we've bought the 7-day pass. Now we don't need to worry about our travels for the next 7 days. So we can just find the min cost for start +7 at this point. And then option C. That's going to be our 30-day pass. So costs index 2 plus. I'm just going to copy and paste this. Our min cost recurse at start +30 because we don't have to worry about costs for the next 30 days. Just make sure I didn't type these wrong. Okay, so now we've explored all three options. Option A, B, and C. That's a 1-day pass, a 7-day pass, and a 30-day pass. Which one do we choose? Well, we'll choose the one that gives us the lowest cost. So we'll just return the minimum of those options. And that's pretty much it for the recursive algorithm. Now the one last thing we have to do is we have to call that recursive function. So out here, we'll call return our min cost tickets recurse for day 1. All right, let's see if this works. Look at that, this works. So let's submit this and see if we can pass all the tests. We don't pass all the tests. All right, so why is this taking so long? Well, option A is going to call pretty much every single number from start to 365. Option B is going to call the same function for pretty much all the same numbers because on day 1, you'll be calling option A on day 2. Option B will call on day 8. But then on day 2, option B will call min cost for day 9 because 2 plus 7 is 9. So you'll be calling the same function so many times. It's going to cost you a lot of time. So how do we mitigate the problem of calling the same function over and over and over again with the same parameters? The simple thing, dynamic programming. So in dynamic programming, if you have the same input with a defined output, you don't have to do the calculation over again. You just cache the value. So when you get the same input again, you return the cached value instead of running the calculation. The simplest way to do that in Python is actually through something called functools. It's a library. So from functools, we can import cache. Now cache is a decorator. It is a function decorator. So you say at cache right here. And that's going to decorate this function with a caching mechanism that acts like our dynamic programming. For the same input, it will return the same output without having to run through the entire calculation again. So that's all you have to do. Let's see if this works. And that does work. All right, let's submit this and see how we do. And we pass. Not very well though. So we passed, but we only beat 18% for runtime and Oh, and 6.94 for memory. Yeah, that's not great. Let's see if we can improve on this. So one thing we can do is we can do our own dynamic programming. Sometimes that's better than running the func tools caching. So I'll show you how to do that now. Let's run our own dynamic programming. So out here, we'll have some DP, and it's an empty dictionary. DP stands for dynamic programming. It's just a way to signal that this thing is going to store our key value pairs for this function. So how do we implement our own caching? Well, the first thing we'll do is we'll say if start is in our DP, then we can just return DP at start. That's pretty straightforward. So if we've already run this calculation and stored its answer in our DP, we'll just return it. So otherwise, we just look for our returns. We're returning right here. So we'll just store that DP. All right, we'll replace this return by storing our value in our DP. And then we'll return the DP at start here. Same thing down here. We can say our DP at start equals this value, and then we'll return our DP at start. All right, let's see if that saves us anything. So it may or may not. Sometimes caching is super fast, sometimes DP is faster. All right, saves us a little bit. So now we're beating 25% for runtime and 26 for memory. Yeah, it's a little bit of an improvement. Okay, what else can we do here? So at this point, we're actually going through every single day from 1 to 365. What if we didn't actually go through every single day, but we just went through the days that are in our days array here? I think that would help, right? So in that case, we'll start on day at index 0, and this will be start index. All right. We don't need this because we're checking the index. We know it's in the days. Okay, but now this has to change. So the start index +1, actually that doesn't need to change. We'll just go to the next value in our days. Now I think we have to go, yes, this is going to be tricky. So our next start, actually I'll do that here. This will be better, yeah, trust me. So our next starting index is going to be our start index +1. So we can just call this start next start. All right, and now we need to find the next start for our 7-day pass. Let's see, that's while next start is less than 365. I guess it could equal. Yeah, less than or equal to 365. And let's see, our days. Oh no, sorry, not 365. It has to be less than or equal to the length of our days. Oh, okay, I might need to store that out here. Let's have something out here. We'll have max index, and that is the length of our days. -1. Yeah, I think that'll be better. So we'll start index is less than our max index, and the days at our next start minus the days at our current start. Let's see, that has to be less than 7. We'll just continue, or we'll advance our next start. Okay, so this is a little bit more confusing, but it's more efficient. So instead of going through days 1 through 365, we're going through the indices of our days here. Now, if our index, actually this shouldn't be 365 anymore, this is going to be our max index. So if our index is out of range, we're just going to return 0. Otherwise, we're going to basically buy the pass for this day, and the next potential day will be at the next day in our list of days. So that's our option A. We're just going to the next day in our list. Option B, however, we might need to skip those days. So we'll check out the next day that's greater than 7 days away from our current day. And that means we can change this guy down here to next start. And we can grab this whole thing, and we'll do the same for option C. Now option C will be 30 days away. And again, we need to change this to our next start. Okay, so now instead of going through every single possible day, we're just going through the days in our list. Sorry, I had to step away for a second. Hopefully the cut won't be too jarring here. Looks like the colors did change, but we should be in the same spot. Okay, finish this up. We still need to change these guys down here to start index and start index. And I think that's good. Oh, one more thing. So we need to go while our next start is less than or equal to our max index. The max index is still a valid index. I think I have to do that down here as well. Okay, let's give this a try. All right, that works. And let's submit this. And we do better. 56% for runtime, 27% for memory. Not too bad. A little bit better. Not a huge improvement, but a little bit of an improvement. Let's try caching again. I'm a little bit curious to see if changing this out for our func_tools cache makes a difference. All right, let's try this again. We don't need this DP anymore. All right, cleans up the code a little bit. Let's see if it makes it any faster. Oh, it does. We're at 63% for runtime, 27% for memory. I really want to get higher than a 63%. I tried to save a little bit of time by cutting out the call to min and writing my own conditionals to get the minimum value for the result, but it didn't really help that much. Not at all. All right, looks like 63% is the best I got today. All right, well, that's it for me today. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.